Hi, and welcome to this applied amines exam question based on problem solving and bringing several chemistry ideas together. So first of all, let's have a look at the information that we're given. There's quite a lot to try and process there, so let's take each bit at a time. You can see there's a reaction scheme at the top, and it gives you a little bit of detail on the reactants and what's being added to which compound. It also tells you a bit about A is a bromoalkane, B is a salt, primary amine is C, and then the first bit of information that you can do something with is the percentage by mass of the elements. So therefore that can be used to work out the empirical formula. And bearing in mind that it's a primary amine, that means it's going to have an NH2 group rather than two alkyl groups or three alkyl groups attached to the nitrogen, as you'd find in secondary and tertiary amine structures. The 2-to-1 ratio of the reaction between C and H2SO4, you need to think about the ratio of the amine group, NH2, to the proton that's incoming, because obviously amines behave as a base. So NH2 to H plus is 1-to-1, and therefore there's two protons that can behave acidically in H2SO4. Each of them would require one amine group, so therefore you're likely to need two amine groups for every sulfate. So that means the structure of D is going to be something along the lines of RNH3 twice, making the amine part, and then SO4 once, making the sulfate part. So we're looking at this sort of structure here. Finally, it says when excess A is added to C, compound E is formed, and E has the molecular formula C9H21N. So the molecular formula suggests a tertiary amine structure. This is because it mentions excess A here, which suggests multiple stages in a reaction to get to compound E. So thinking about multiple substitutions in amine synthesis, you can start to see how this might work. So let's do the calculation for the empirical formula first. So dividing percentage by the relative atomic mass of each element, we get these numbers. And dividing by the smallest component, which is 1.692857 ... we get a 3-to-9-to-1 ratio. So the empirical formula for compound C is C3H9N. So bearing in mind it's a primary amine, like we said from the question, it's possibly that CH3, CH2, CH2, NH2 is a potential candidate for the structure. So now we know that we've got a primary amine with a propyl group next to it. We can come back to this idea of salt D and work out what it might be. So thinking about R being C3H7, then C3H7NH3 twice in the structure that we've come up with already would suggest that salt D is C3H7NH3 2SO4. So working backwards along the reaction scheme from D through to C, through to B, through to A, thinking about what the addition of sodium hydroxide, the role of this in an amine synthesis, an aliphatic amine synthesis, is the removal of the proton from the salt so that the salt can become an amine. So that must mean B is an alkyl ammonium salt, alkyl ammonium bromide, because it says bromoalkane A, so A must be C3H7Br. So suddenly a lot of things fall into place once we've worked out one or two of these structures. So just to recap there, NaOH converts the alkyl ammonium salt to the amine, so B must be the alkyl ammonium salt. And NH3 is acting as a nucleophile to make the alkyl ammonium salt in the first place, so A must be a bromoalkane with the same organic carbon chain as B, in other words C3H7. So let's now tackle what C9H21N might be. We already thought about it possibly being a tertiary amine. So they now want the structures for A, B, C, D, and E. So that's our A, C3H7Br. That's B with the NH3 plus Br minus. That's C with the NH2 attached to the propyl group. And then you've got your tertiary structure of amine E and also the salt D. So they also want you to name them. So we've got those marks there as well. So now they want the mechanism. It's a straightforward nucleophilic substitution. Don't worry about what happens when the sodium hydroxide reacts with the alkyl ammonium salt. They're not interested in the curly arrow part of that. It's literally just the part here. That's the same as a normal nucleophilic substitution, except NH3 is your nucleophile with the lone pair on the nitrogen being donated to a data covalent bond on that carbon that's now formed here. So, thinking about question 5, we know what B is already, so we just react B with NaOH to make the amine, sodium bromide, and water. So that gets those 2 marks. So E, like we've said already, is a tertiary amine. So now we need to do our 3 equations. I'm going to make some space at the top here. So if we cancel out the C3H7 that allows us to add those 2 equations together, because those 2 things happen in 2 stages. So the Brown equation is your first one, and then the remaining 2 are here and here. So that gets us our 3 marks for the final part. Okay, thanks for listening. Until next time, see you soon.